Today I'm going to talk more about something that, as Brian said, we uncovered in data from the GALEX mission, which is no longer in operation, and the steps we took to try to understand what exactly this thing was and what caused it and what we can learn about it. Just a quick overview, in case you're not familiar with what GALEX was. GALEX stands for the Galaxy Evolution Explorer. It was a small explorer mission. It was dedicated to studying the sky in ultraviolet light. Its primary mission, though, was really to understand how galaxies form stars over time. And so it studied local galaxies and their UV properties, connected them with the physical properties of galaxies we observe in optical, infrared, and radio, to help build a calibration set that we can then apply that to galaxies over a span of about 10 billion years. And so we can map the cosmic histories and star formation histories of galaxies over time in this way. GALEX consisted of two imaging channels in the ultraviolet, which we call the far ultraviolet or FUV, and the near ultraviolet or NUV. And I'm just listing their wavelength ranges here. These are the energies of photons that they cover. It also includes a low resolution slitless spectrograph. So I'm going to actually show you an image of what this looks like later. Its operation was about 10 years, about a decade. It did pretty well. It covered about 70% of the sky in the far ultraviolet, near ultraviolet. And just for reference, this is the electromagnetic spectrum. Ultraviolet is here, a little bit left or shortward in wavelength of visible. So it's kind of where we're focusing our attention. But importantly, GALEX, because it studied most of the sky, it didn't just study galaxies outside of, galaxies that are not just our galaxy, but they studied stuff in our galaxy as well. And it discovered a number of strange phenomena that were recorded over, the years during its operation. One of the first ones was this really strange far ultraviolet tail from a runaway AGB star, or actually a binary star, that turned out to be actually, this is important. We're going to point back to this example later, but this was a phenomenon that we would not have seen before if we'd not looked at the ultraviolet. We've also discovered things like astrospheres around other stars, really similar to our own sun's heliosphere. This was the first time we actually caught these around other stars, though, besides our sun. And remnants and shocks from novae or past novae events. So there's lots of really cool information that we were discovering in our own galaxy from GALEX. GALEX, this is not a great picture, but hopefully you'll see it in a second. GALEX, though, took some really, really deep images of particular parts of the sky. And this is one of those. And in this popped out this really strange object, this really diffuse, fuzzy far ultraviolet ring that we ended up calling the Blue Ring Nebula because of the color scale that the GALEX ended up using for far and near ultraviolet bands. The far ultraviolet was typically shown in blue, and then the near ultraviolet in a yellow color. So this is it in the image. Oh yeah, so kind of see it there. So you can imagine how faint this thing is, right? This is one of the deepest images that GALEX took, and still it's we barely. Okay, great. So the Blue Ring Nebula, what we ended up calling this thing is this ring-like shape surrounding a bright near ultraviolet star, and so. Really bizarre. We'd never seen anything like it. So we really wanted to understand what it was, why it's even there. And then we'll go through, when we finally understand why it's there, why we should care, and then what might come next in studying these kinds of objects. So I like to just put this as a reference on scale in the sky. This thing extends about 8 arc minutes in the sky. And if we were to compare this to other kinds of nebulae that we see in the sky, these are all kind of scaled against the 8 arc minutes of the Blue Ring Nebula. So it's on scale on the sky to some of these planetary nebulae and supernova remnants, if not a little bit bigger. And then sometimes in my other classes, I like to show it compared to the moon. It's a quarter the size of the moon on the sky. So what is this? How does this thing emit light? So what we know, we've seen this in the far ultraviolet with GALEX. So that, again, that's the bandpass for GALEX. And along this western edge, we see both a near ultraviolet and a far ultraviolet component. It's very faint, but it is there. And so this spans really the range of ultraviolet light. So let's look at it in other bands as well. If we look at it from the UV through the infrared, what do we see? When we're looking for this nebulae, really we only see in the far ultraviolet here this broad diffuse ring of glowing emission. If we look anywhere else, there's not really anything compelling there that really matches what we see. But in the far ultraviolet, near ultraviolet, and in a narrow band filter of H alpha, which covers a hydrogen emission line, we see this filamentary structure that kind of outlines the western side of the nebula. And in H alpha, even you get a little bit more structure that appears a little bit further westward of that. It's also worth noting that we did serendipitously cover part of the Blue Ring Nebula with Chandra, and there were some detections that were reported a couple of years after our original publication on X-ray emission from parts of this filament. Okay, so let's start with the far ultraviolet ring. How does that emit light? Well, let's go back to our example of this star, the shooting star that we caught in the far ultraviolet. And in this case, the far ultraviolet light was attributed to molecular hydrogen fluorescence. So this process is when we have molecular hydrogen that's found in its ground electronic band. So it kind of likes to sit there most of the time when possible. But sometimes things happen where, especially if it receives energy from some source, where it can get kicked up into a very excited electronic band. This is different than how we normally think about molecules emitting. A lot of times when we see molecules like in the radio and the infrared, their transitions are really just happening between vibration and rotation, quantized levels within this ground electronic band. But you can kick up these molecules with energy sources, non-thermal energy sources, that result in a fluorescence process. So what this looks like is if you give molecular hydrogen, say in one of these bands in the ground state, enough energy, which in this case, the energy differential between the ground and this excited band is an FUV photon, it'll kick up into the state here and then have to release a photon back down to the ground band in order to relax back down to this ground state. And this release, because this difference in energy corresponds to about the energy of an FUV photon, results in the release of a UV photon. And so molecular hydrogen really releases a lot of fluorescence photons in the ultraviolet band. So we see lots and lots of lines that show up because that transition I showed resulted in just one fluorescence, but from any given state, here, any given quantized state in the electronic band, it has many different routes back down to the ground state. So there are different kinds of energy sources we can have, and we'll talk about that in a second. But this is a real spectrum of molecular hydrogen emission, in this case from a protostar with a protoplanetary disk that has lots of molecular hydrogen. And all of these green diamonds are pointing to molecular hydrogen fluorescence or emission that arises from this process that I just described. So there are different kinds of energy sources that can produce this fluorescent emission spectrum of molecular hydrogen in a UV. It can be radiation, whether it's a UV background or say a specific line like Lyman alpha that's produced by hydrogen can excite H2, a specific H2 spectrum. Or you can have collisions like with electrons or cosmic rays, and those will create a different kind of spectrum. There are similarities between these, but by eye, you can notice that there are differences as well, particularly with the different intensity levels of features that do pop up. So we can use this information to try to diagnose what's happening with the Blue Ring Nebula, assuming it is molecular hydrogen that is creating this far ultraviolet only spectrum. So like I said, GALEX had a low resolution slitless spectrograph mode on it. And so out of curiosity, figure out if molecular hydrogen is indeed the cause here of this emission. It took a slitless spectrum, and that's what it looks like here. So the blue is the zero order, or just the image in the ultraviolet. And the orange is the grism, or the spectra of our nebula and the other stars in the field. Because it's a slitless spectrograph, we don't have a really nice resolved spectrum of this thing. It just kind of smears out. But what we do notice is that our emission of the spectrum really starts to kick in at around 1600 angstroms, which corresponds roughly with about this peak in emission that we see on the longer wavelength end of our molecular hydrogen spectrum. The 1550 angstroms was noted because if this was something else, say a carbon line, then we should have expected the emission to show up around there, but it doesn't really show up until a little bit later. So we can take the spectra that we can predict, like what I showed in the previous slide, and convolve that with this very low resolution of GALEX, and see which likely source might be creating the molecular hydrogen emission, in this case of the Blue Ring Nebula. And really it's this case of a collisionally excited H2 population that best matches that really low resolution spectrum. Again, we're working with really limited data here, so that just by comparing the relative peaks and where we expect emission to arise, this really is like more indicative of that emission in the longer wavelength end of our range than, say, a UV pumped source. Okay, so it seems to be molecular hydrogen. It seems to be collisionally excited. Let's look now at what's happening with these filamentary features. If collisionally excited, this could be well in line with a shock front, right? And we see this in multiple different wavebands as well. So we went after this actually on the ground with LRIS on Keck, and took different, used the multi-object spectrograph there to take different slit positions in the spectrograph. Along the slit on this western edge, we had 4 different slits, and then 2 more on this lower southwest edge as well, to see what kind of, to see what the edge alpha lines were doing here. And when we did that, this is a figure of the relative flux measured at each of these slits as a function of velocity, or velocity from this heliocentric center. And what we measured was that this seems to be in line with something moving on order of hundreds of kilometers per second, upwards of 400 kilometers per second. This edge that is the western part here seems to be coming towards us. It's blue shifted, while the 2 slit positions down below appear to be red shifted, moving away from us. And so we envision this picture of, okay, well, maybe we have this cone of material that's been ejected, say, from this bright star at the center here, that is ramming into the interstellar medium now, and this edge is leading or coming towards us, and this one is trailing. So we're seeing kind of the orientation of the two biconical outflow components of from the star. Right, so if true, could this be in line with things that we're kind of familiar with, say, like planetary nebulae? Well, not really, because these tend to have much slower velocities. They're maybe upwards of 100 kilometers per second, but they tend to be a little bit slower than that. And supernovae tend to be a lot faster, so I think thousands of kilometers per second. Okay, so let's quickly just go over what we know so far. We have a fairly large nebulae on the sky that has apparently a collisionally excited molecular hydrogen outflow that's moving at about 400 kilometers per second and seems to be characterized pretty well by a biconical outflow that starts from this star at the center here. This star has a name. It's really catchy, TYC 2597735 So I'll probably just call it TYC or something from now on. It's a lot. But we can start to gather some information about it we can, for example, get the distance and the distance from the Gaia data release 2 and data release 3 are pretty consistent. It's about 1.5 to 2 kiloparsecs away. Using that information and the size of this object on the sky, we can use the sky size and take a rough estimate of the velocity, say 400 kilometers per second, to trace back the time that this might have started. And we come up with about a 5,000 year start time. So whatever happened to create this nebula seems to have happened about 5,000 years ago, give or take. We can also measure the luminosity of the Blue Ring Nebula. We can estimate that from our simulated spectrum, and we get about 10 to the 33 ergs per second in luminosity. And we can back out, assuming this is a fairly optically thin nebula, that this might contain somewhere around 4 Jupiter masses of material that's emitting. Okay, so let's look back now on the star. Again, here's our view of UV through the infrared. And instead of focusing on the nebula now, let's look at what's happening with the star. Okay, so we notice in the far ultraviolet, it's kind of faint, especially compared to the near ultraviolet, it seems to perk up a little. In the optical, it does seem to be fairly consistent. And then as we get into the infrared, it seems to brighten a bit. And also worth noting, it is detected in X-ray as well. Okay, so instead of looking at this by eye though, let's actually quantify this and we can create a spectral energy distribution to help us figure out what's happening from the ultraviolet through the infrared. The intensity measured in each of these photometric bands. And we see a pretty consistent stellar black body emission profile for the star, and then this extra infrared flux appears. So that's pretty interesting. Let's focus on that for a second and think about what can create that. And the first thing that kind of comes to mind is, well, forming stars with disks can create this kind of signature. They tend to have infrared excess as they're building up, because they're blocked by lots of dust and they have an envelope. As they're beginning to form, they clear that away and they're left with their remnant disk where they're forming planets. They still have the infrared excess because of that emission from the disk where planets are forming. And then as it builds, the star builds up further from that disk, planets build up and that begins to clear, that disk component in the infrared begins to go away. So, okay, that's interesting. Maybe what we're working with is protoplanetary disk. So let's think about other things we can look for to see if that could be the case. So we have an infrared excess, excellent. These kinds of systems also tend to be highly active. So we'll see signs of maybe higher energy continuum than we expect. In the UV, for example, we actually measure compared to a stellar photosphere model, about 100 to 1,000 times more FUV flux than we expect here. So maybe it has an elevated UV continuum, but maybe the kicker here is that in the X-ray, we do actually detect a strong X-ray component. So that could be our higher energy level as well. So we seem to have something indicative of a higher energy continuum. And then if we look at line emission, in the optical, we actually do have a pretty decent H alpha emission signal from the star. And the signal actually varies over time. So we took a time series at different points of time of the H alpha emission profile, and it seems to kind of sway. So these are just bisector points that show its movement over a period of a couple of months. And so we seem to have all these sort of telltale signs that, okay, maybe this is actually a really young star. So again, just to highlight some of the points we've already gone through. So this star, TYC 2597, is at the center of the Blue Ring Nebula that appears to be moving at about 400 kilometers per second towards and away from the star. It looks on face value like a pre-main sequence star with a planet-forming disk. So could this Blue Ring Nebula be some sort of giant outflow or jet from an episode of accretion? Well, it doesn't appear likely. When we look at examples of other kinds of young stars that have these jets and these like clumpy outflows, they appear multi-wavelength. So we should expect to see other kinds of signal from the Blue Ring Nebula, but we don't. And the velocities of these things also don't match. These jets tend to be an order of 100 kilometers per second. The Blue Ring Nebula, again, is too fast for that. So it's probably not this. And probably the kicker here is that while TYC 2597 does have excess X-ray emission, it's actually not really in line with the majority of pre-main sequence star relations. So if we were to compare this X-ray luminosity to the period of the star, our star here is way down here compared to where the majority of the pre-main sequence stars are. In fact, TYC seems to be a little bit more in line with main sequence stars. So it's still a little bit off from pre-main sequence stars. So maybe this isn't quite it, but probably, again, another piece of evidence that kind of goes against this is where TYC 2597 is in our galaxy. So if we were to place this in our galactic plane, it would be located way up here above the galactic plane, about 1.5 kiloparsecs or so. So TYC isn't really near any star forming regions. It doesn't mean it couldn't have formed out there, but it also doesn't have any velocity motions that suggest that it was flung from any star forming regions. It just appears highly unlikely that it could be a relatively new star. Okay, so this seems to be not likely. So what else can we learn about the star then to give us another hint of what it could be? Well, we can use information about its distance, the special energy distribution, as well as high resolution spectra we got from Keck high-res, and interstellar and circumstellar reddening along the line of sight to back out some stellar parameters to see, okay, where are we sitting with like the basic properties of these stars. And we see that it's a star that's about, roughly in line with the temperature of our own sun. It's about 100 times more luminous. It's got a kind of a fluffy-ish surface gravity, about 1 to 2 solar masses in mass, and has a metallicity that's quite low, almost a whole dex below the sun. So when we fit our stellar models to this, two kinds of stars seem to fit best to the spectra of the star, either a pre-main sequence star, which might not be, or a recent post-main sequence star. So if we go that route and we compare TYC 2597 to other kinds of stars in this kind of evolutionary stage, say comparing its surface gravity to the temperature, it appears mostly in line with the populations here, but still a little bit off. So what could cause that? Well, potentially something like a common envelope event might cause that. It would require a pair of stars, so like binary stars, those are quite common. And at some point in this, in their evolution, they would come close enough to interact and exchange material through Roche-Loeb exchange like this, and could eventually lead to, say, a merging or a collision of stars. And this is just one more recent example that I think Brian is very familiar with. So, okay, a stellar merger might actually make sense because they do have outflows. Those are quite common from these kinds of things, and they tend to be on order of about the velocity that we measured for the blue ring. And evolutionary models of mergers, they actually support these kind of weird, kind of slightly off characteristics of stars after they've undergone these events, which is what we're seeing from TYC 2597. And we have these circumstellar environment of TYC. This infrared excess in particular could easily be explained by this Roche-Loeb exchange, and leaving material left behind in that regime. So, okay, what are the series of events that could have happened then to explain TYC today and the Blue Ring Nebula? So we drew up these little cartoons for how we envisioned the past of this the past of this event happening. We had our primary star, now TYC, evolving off of the main sequence. It would start to expand its envelope and begin to drag in a companion who may have been orbiting pretty close to the star, to a point where now the companion can begin to strip the outer envelope of the star and create this bound disk of debris around it, until finally the companion and the star collide and create this release of energy that expels a whole bunch of matter out into space. We have a bound disk left over, as well as an expansion of atomic, as well as dust and molecules out into space over time, until today. We have what's left over and what we see, this primarily just molecular hydrogen outflow, a shock with the ISM to explain those filamentary structures, and then whatever is left happening around the star. It could be a lot of activity, either through accretion, interaction with the bound material remaining around it, or from it just still settling from this whole event. So we worked with somebody that was really familiar with MESA to help us predict what kind of progenitor system would help explain why TYC looks the way it does today, if this were the case. And what he found was that we could really well reproduce a lot of our observables, the temperature of the star, the surface gravity, and the luminosity today, with about a 5 solar radii expansion of a 2 solar mass star, colliding with a 0.1 solar mass companion. So these are the best fit parameters for this progenitor model. And what we had left out of this as well was a prediction of, if this did happen at that point in time, what kind of dimming we might expect to see today. And it turns out this is measurable. And so looking back over 100 years, we could monitor and measure the dimming of this star over time. And our prediction was about a magnitude brightness dimming of a 0.1 per century. And that actually is not too far off when we actually measure. So promising. So now the question, one question that remains is whether if it collided with a companion, would that companion have survived? So is there still a companion orbiting the star? So we could use the transit method. There are lots of pros to this. You can observe a dimming when the companion goes in front of the star, and that light dimming is proportional to the size of your companion. So if we had a 0.1 solar mass object orbiting like a 1 to 2 solar mass star, you could probably detect that pretty easily. But the problem is the orientation. So the Blue Ring Nebula tells us that this object is almost face on, and so the orbital plane is not even going to allow us to see this kind of transit for this particular object. So that's out. But another method we could use is radial velocity. This tracks how a star's colors, when we take the spectrum of it, wiggle over time. It's very sensitive and kind of orientation agnostic. So there is a sin I component to it, but as long as that inclination angle is not 0, we should be able to still see that wiggle of lines from a companion. It requires high-risk spectral resolution, which we can get here from the ground. And so we use a combination of Keck high-res in about 12 years ago to do this radial velocity. We also used the HPF, I think, that was out of Penn State in order to confirm the results that we got with Keck. So this is the radial velocity signal with the Keck high-res instrument. And from this signal, we could constrain the range of a potential companion remaining in orbit around the star. So the range and where it would be located, so the semi-major axis. And the range is about of order a little bit over a Jupiter mass, but less than a brown dwarf. But again, the minimum we needed to eject the Blue Ring Nebula is way up here. So likely, if there is a companion still in orbit around TYC 2597, it's not the companion that created the Blue Ring Nebula. But, okay, and the other kicker here is that we did an analysis between the radial velocity and basically the level of stellar activity from the star and found a really tight correlation. So likely, this radial velocity that we're measuring here is due to activity happening at the star and not necessarily companion. So this is a strong indicator that this signal is actually stellar activity and maybe not companion after all. So possibly there's not a surviving companion, which is kind of cool. So why do we care? Well, if what we claim is true, TYC 2597 could be our first example of a complete stellar merger that we can observe directly. Okay, so asterisks here because we've gotten into trouble for this, but basically, like, TYC is not hidden anymore. So when these things go off, originally they quickly become obscured from view. They're very dusty, and you can no longer see what's happening with the remnant left behind. But we have very little reddening to TYC 2597. And even though it's several thousand years after it's happened, we still see these signs that it is still not very happy. It's still not quite equalized. So if we have like this little timeline of a stellar merger or common envelope event, we have plenty of examples of stars where we think like they're going to undergo this kind of event, if not soon, then over the next however many years or so. We have lots of events now where we think we've caught these mergers happening, and then they quickly become blocked from view. And then we have to wait thousands of years for something like the Blue Ring Nebula and TYC 2597 to appear, and we get a clear view of what's happening with the system. And then we have to wait however many longer years before the system finally settles, and then you're left with whatever's left over. So it's a nice stepping stone now between us catching them when they happen and these stars that we think have evolved from collisions in the past. So these are important because lots and lots of stars out there have companions and likely go through these kinds of events. That's why there's lots of different kinds of systems that people study having gone through these. They are a connection between these peculiar stars and stellar populations that don't quite follow our standard predictions of stars and stellar characteristics, and potentially might lead to multi-generational planet formation. This is a big question mark, but there are some systems like white dwarfs where it's really hard to explain why they have certain kinds of planets in orbit around them. Okay, so what comes next? So there's a lot of information that we've learned and gathered from observations today, but there's still so much that we don't know and are trying to understand. And we could with current facilities like HST or JWST. So if we want to know more about TOIC 2597 and kind of the outstanding questions arising from that, I think a big one is whether the infrared excess that we're observing really is coming from a disk, and if so, what the characteristics of that disk are. That one's highly uncertain. And that's something that JWST can help us illuminate by directly studying the dust distribution of that infrared excess, telling us the composition of it, also giving us access to lots of different kinds of molecules and gas that could be related to that, that disk. But also HST and the UV gives us lots of information about not just the star itself, but also the disk. So with the star, we could differentiate between whether that star is still creating matter from a bound disk or bound material, or if all the activity we're seeing is really just chromospheric related. We could tell whether or not we still have jets or outflows or winds from launched from the system. And unlike JWST, we could have the resolution to resolve, if there's a gas component to the disk, we could resolve the actual inner rim of this disk. For the Blue Ring Nebula, there are lots of questions I think that we would really like answered, because it'll help us understand if there are more of these out there and if we can catch them like soon. So understanding what the properties of this thing are is, and relate that to how long we expect it to last is really important. And the big question is, are there more out there that we can discover? So I think I wanted to highlight this because we recently got awarded HST time to study the Blue Ring Nebula, specifically to measure the column density of hydrogen through a sightline of it, where there's like a really nicely placed UV bright galaxy behind the Blue Ring. So we can use that galaxy in the background to help us get an absorption line spectrum of through the Blue Ring Nebula. And we can use that information to help figure out just how much hydrogen is there, back out what the mass of the nebula might be from that, and based on dissociation rates from the populations of H2 that are probed through the sightline, just how long it could last. And then thinking ahead, we have upcoming UV missions like UVEX, which will cover the whole sky in the same bands that GALEX did, but at 50 times deeper over the mission lifetime, and could help us discover more of these. So at the end of our paper on the Blue Ring Nebula, we predicted, based on rates of these things going off, that we could have upwards of 10 Blue Ring Nebula in view right now, but we just haven't found them yet because we haven't looked deep enough and we haven't looked at enough of the sky. So UVEX might help us actually uncover more of these examples. And then thinking a little bit further ahead to a mission that I'm working on, a far-ultraviolet high-resolution spectrograph concept that would study diffuse objects, primarily things like molecular clouds and star-forming regions, but is specifically designed to study fluorescent molecular hydrogen in the UV, and would be an excellent resource to use to help us to diagnose the properties of other Blue Ring Nebula if they're out there, as well as this one, and help us understand how long they expect to stick around. Okay, so in conclusion, so we found this Blue Ring Nebula that appears to be this outflow that is being illuminated now by molecular hydrogen fluorescence. It's there because of a past stellar merger we think happened thousands of years ago. These kinds of objects, they reveal these like an intermediate stage in this merger evolution process, and to date did not have any observational constraints, but now we're starting to get them because of this one example. And there's lots of remaining questions that current and future telescopes can help us answer still. So we're still, trying to go after those and figure those out. So thank you.
Questions? Start on this side. For an object like this, like a stellar merger just after the merger, what do you expect for, like, if I took a spectrum of that star, what would you expect of the stellar parameters I derive? Would it look strange? Would it look like it's on the main sequence and just like a more massive star? Like, are there any signatures you expect?
Yeah, so some things that we have observed from optical spectra, we've observed line broadening that kind of looks like not like a typical Doppler line broadening, but like almost an extra component. And so that was kind of attributed to like large scale turbulence happening potentially at the surface of the star. We see a lot of signatures of absorption lines that look really similar to like a main sequence star, but then every once in a while we see like H alpha, an emission that doesn't quite make sense when you compare it to that. So it, like, for the most part, I think like 80% of the spectrum, you probably are like, oh, this is like a normal star. But then they're like, when you look more closely, there are like kind of peculiar things off by it.
Because oddly, Apogee took a spectrum of this star.
Really?
For some reason.
Oh.
In 2020, though, so maybe it was in response to your paper.
Oh, maybe.
It's very strange.
Oh.
But I don't know if there's anything to learn from that.
Oh, cool.
But if there is, then maybe you could find them in the other Apogee data.
Maybe. Yeah. Okay.
Yeah.
So thank you for that very beautiful description of this source, amazing kind of thing. I was wondering whether you've thought about possibly observing it with near-infrared spectrograph to look through the infrared hydrogen lines, molecular hydrogen lines that are inevitable. Because as you described, I mean, this fluorescence process leaves the hydrogen in its ground electronic state, but excited vibrationally. So there's inevitable quadrupole emission, and you could probably get a whole map of it. You wouldn't need a background source. You could just directly measure the molecular hydrogen column that is that way. Yeah. So are you planning to do that?
Yes, that's one of the, I cut it because I thought my talk was too long. But that's one of the ways we could use JWST. Yeah. Yes. So either with the imaging or with multi-slit spectra, we could use especially like MIRI. We could also use some of the shorter wavelengths to, like you said, build almost like a column density versus temperature diagram and
the different excitation mechanisms that you mentioned, for example, electric collisions with energetic electrons, or excitation via Raman alpha, or continuum UV radiation. Each of those create a different infrared spectrum. Yeah. So you'd be able to distinguish between these mechanisms, and it's very clean. And it's inevitable. Yeah. I mean, those lines are certainly there.
They are. It's just the matter of how bright they are.
Well, you can calculate that easily because you know the UV, you know the infrared. They're directly linked. Yes, and the only way to get them is with JWST, basically. Yeah. You couldn't do it from the ground?
No. So I figured, so when I first saw this thing in the UV, that was the first thing I did because I had access to Keck. And so I wanted to use near infrared, like a multi-object spectrograph or something to get, or a long slit or something to get the infrared spectrum, but it's too faint even for the best case scenario.
Okay, it's a little bit surprising. I mean, for example, in IC63, you can see both. See the UV and the infrared. So I'm a little bit surprised that you can't see these.
I don't doubt the infrared is there.
I'm surprised that you can't see them
from the ground. Yeah. Okay, anyway.
And that was very lovely. So one of the things I'm struck by, and I just may not have the right physical picture, was just the smoothness of the emission, given everything that's going on. And I want to make sure I understand. So is the molecular hydrogen like stuff that's forming at an interface of the outflow, or is it something where it's more like it's there and it's being illuminated? Like, and why is it so smooth? Or is it so smooth because it's a very high latitude, so there's so much ISM that's running in? I'm stuck on the smoothness
Yes,
and
I
trying to see how
know.
it fits in with the picture.
Yeah. So here, so yeah, so you're talking about the smoothness of this like main component. I think probably the best way that I've been able to think about it is because of this overlapping cone area. If we're not really seeing the emission here or here, but the parts here where they overlap, it just is bright enough to show up. And I'm not really I'm not really sure why it's so smooth. It could be the properties of the outflow itself. Maybe it happened and it was a very like homogeneous outflow. I don't know. Or like happened over like a span of time and then kind of stopped. And so you get kind of like a uniform distribution as it's expanding through space.
Right, so it has to be some steady kind of outflow during that event. And then is the UV radiation primarily coming from the star that did the emission, or is it background UV emission? What's driving what's pumping the hydrogen up?
The pumping of the hydrogen might actually be the shock, the collision of the electrons as the outflow is moving through.
So I think that's why it could be, because the shock is heating up these electrons and they're kind of volumetrically like heating up the H2. So I think to get a smooth profile, you need a smooth density distribution of H2, but the electrons I think can kind of freely go through this whole region.
I mean, if you can find more of these, it'll be interesting to see whether it's a feature of being at high latitude where, you've got a fairly uncomplicated environment to do your outflow into. Like, it's going to look very, very different.
That's right.
Because the molecules are formed quite early, like in the stellar mergers we see in real time, the molecules are forming in like decades. So this is they form and it's kind of expanding quite a bit before this happens.
Yeah.
There was Amy. Sorry, not Amy. Sorry, you had your mask on, so I could.
Sorry. So as you showed the non-shocked and shocked ISM, so that kind of reminded me of, as you made the analog to astrospheres, like our own heliosphere. And we know that there's, the termination shock, and there are a lot of those ENAs produced. And we have the structures like the ribbon, and there are missions who does investigate those. So I was thinking, are those filaments, those analog of the ENAs and the structure that get produced? And if so, whether we can ask those missions like IMAP or the analog of previous IBEX to investigate those kind of structures that may show up there.
I'm not sure. Are you saying that like they might be structures of the
energetic atoms that form on those shock boundaries?
Yeah.
And when there's a heliopause and the termination shock, those energetic atoms form like whatever it was, the IBEX, the Interstellar Boundary Explorer, the NASA mission that was sent to investigate that. It found the ribbon, which was the structure made out of those hydrogen, the energetic neutral atoms. And it kind of feels a little bit similar to this, the non-shocked ISM and the shocked ISM at the boundary, especially sorry, this is definitely not my area, but it just sounds very familiar that the H. Lyman lines are visible too. And I was wondering, the IMAP mission gets sent into space, well, this year, I think, and it's going to observe our heliosphere, but if a similar kind of thing were to investigate, say, this nebulae, whether it could say something more about the filaments like that.
Maybe, I guess it depends on how sensitive it is. Yeah.
That I don't know.
Yeah, I don't know either. It's quite faint.
So the IR SCE, it looked like it pretty short wavelength. I was wondering what the effective dust temperature is and whether that, that provides any useful information to constrain physics.
Oh yeah. Okay. It's in my paper. I know. Okay, so we did have an effective dust temperature, and I think it was like a high hundreds of Kelvin. So yes, it did help us like constrain it to like at least a few AU from the star. And we did get a very, very rough mass estimate of it as well. Otherwise, like it's very highly constrained and unconstrained. And I think part of it as well is that it appears to fall off yeah. So this, like we could, get an effective dust temperature from this peak here that describes the infrared excess black body emission, but it's unclear if there's like a colder component as well further out. We just have upper limits for that right now. Yeah.
Yeah, I guess it's interesting how this matter, if it's ejected from the L2 point, I guess it would have to like viscously, the disk would have to viscously spread, or it'd have to be, maybe the merger sort of matter was falling back or something to get it all the way out.
Yes.
That large scale.
Yeah.
Maybe I can take my prerogative to ask a question. So in the stellar mergers that we see real time, where we do see molecules form, we do see a lot of dust form. And actually, I heard a talk earlier today suggesting these could compete with supernova as dust factories because the rates of stellar mergers turns out are about the same as the core collapse rate, and they may eject a similar amount of dust. But the big question was kind of, does that dust survive when it goes through one of these shocks? And I'm struck by the fact we do see the molecules dissociating. We don't see any evidence for dust through this ring, but I don't know if we would expect to if it had the same mass.
Right.
So I guess, is there any hope if there to measure actual dust in the, if it were present in the conical part, and or if it were being destroyed? How is there any way to study that?
Well, so actually that's funny because the last time I gave this talk, I had an argument with somebody that they're like, no, there's dust there. So in the WISE images, he argued that wide field W3, the filter, potentially.
That there's a detection there?
Yeah, that there's a detection there. I don't know, but maybe, but I'm not familiar with enough with the WISE instrument to say whether or not, and I think he was more so. But I think our best bet would probably be JWST again. There are, especially if you want to go for like filters that target specific kinds of flavors of dust, like pHs or silicates, depending on what we expect to be formed in these outflows. That might be our best bet. Yeah.
All right. One more question. Is there a particular reason that objects in this phase of merger evolution should be particularly rare? Like, why haven't we seen others like this?
That's a great question. I mean, at this point, if TOIC 2597 didn't have the blue ring around it, I don't think we would have ever caught it. It's already hiding really well as like a field spar, right? So maybe it comes down to like, how long does something like a blue ring last? How long does something in that kind of stage last? And you can catch it given it enough time for the star to now be like unveiled from behind the dust, basically. So I think it's a timing thing. And there's a big open question about how long this is gonna, stay emitting, because there's still a lot of questions about how much exactly is there.
But just to comment on that, the fact that it's so far out of the plane is largely what makes it so detectable as well, right?
Yeah, that helps tremendously. But like Emil said, if we can get to the infrared instead and show like these things emitting in the infrared, theoretically like an infrared mission or a surveyor should be able to capture more of these.
It must be rare to have stars that are out of the plane, like you said, with dust disks around them. So you would think maybe like doing some cut on the colors, you'd be able to identify some from the stellar spectra.
That's true. Yeah, that's true.
I don't know if anyone's looking Any last questions? Not, let's thank Keri again.